thanks a lot for the invitation, and thanks for putting together this this nice conference. In this talk, I will be talking about a set of topics which are based on the following set of papers, namely some paper from myself from last fall, and then two works together with Brice Bastien and Damian van der Heijsteek. And I will also spend some time discussing upcoming work with Erik Blauschin and Damian van der Heijsteek, and three well-known mathematicians, Christian Schnell, Ben Bakker, and Jakob Zimmermann. So let's get started. I think it's good to first place my topic into kind of what kind of direction I want to go to. Namely, I want to talk about aspects of the so-called Swampland program. And what is the idea of this program? Well, one wants to identify general principles that have to be satisfied in an effective theory to be compatible with quantum gravity. So I give you an effective theory, which might be somewhere in this blob here. And then there is a subset of these effective theories which are consistent with quantum gravity, and these we call the landscape. And then there might be other effective theories which seem to be consistent, but they are actually not, because if you couple them to quantum gravity, they're just kind of some hidden inconsistencies. So that's the direction I want to go in. And let me now be a little bit more precise. In this talk, I focus mostly on field spaces and scalar potentials in effective theories. So I will consider an effective theory at some cutoff scale lambda, and then this effective theory, it might have some scalar fields, which I call phi here, and some field space M. Yeah, the M will always be the kind of the scalar field space. And these scalar fields, they might be constrained by a scalar potential V of phi, which you can think of as a map from this field space M to the real line. And one of the questions you might ask, and of course that was something which was studied recently a lot, is which field spaces M can appear in the landscape? Well, this was not studied that much, but the question was asked which scalar potentials V of phi can be arising from consistently with quantum gravity. Yeah. Of course, these two questions are related when we lower the cutoff. Namely, we can start with an effective theory which has some field space M, and then we can lower the cutoff. And then it might be that some of the fields are now too heavy to be still part of the effective theory, and we rather should integrate them out. And if we integrate them out, then the resulting field space M1 could be of lower dimension. Right? The previous one was one-dimensional, now the previous one was two-dimensional, now it's one-dimensional. And there could be also many different ways of looking at this previous potential and kind of reducing to this theory with lower cutoff. And you might even lower the cutoff even further, and then you have to integrate out even more fields. Maybe you just have to keep the massless fields if the cutoff is sufficiently low. And then your new field space might be just point-like. So your fields are actually stabilized. So they are set to their actual vacuum value. And maybe there's no flat direction remaining in some cases, or in other cases, there might be a flat direction remaining. So now, if you think about this picture, you might ask, well, if I ask about string theory or quantum gravity in general, we can ask, is the number of distinct effective theories compatible with quantum gravity finite? Of course, this is long part of the string phenomenology program. I think I don't have to explain why this is the case in detail, because it's clear that if you have infinitely many choices, then kind of a statistical arguments, for example, make little sense, or any precise statement about I checked something in 3 or 4 cases is not so relevant if you have infinitely many cases which you would have to check. And so it's an important question for a long time, and there have been a lot of works on this question, including a much recent activity where it was studied the finiteness of spectra, rungs of gauge groups, and so on. In this talk, I will end up in the last part. Well, in the middle of this talk, I will indicate a non-trivial finiteness proof. So I will exactly address one of these finiteness questions, and I will argue that one can mathematically prove finiteness. And then, guided by this success, I will claim at the last part of the talk that finiteness should be promoted to a universal principle to constrain effective theories. So why is that exciting? Well, finiteness is something which is independent of supersymmetry. This principle which I mentioned, it has nothing to do with holomorphicity and all of these things which you might question as someone who says, well, supersymmetry has not been detected and is not a relevant concept for many of these questions. So this is the motivation, the few words of motivation. Now let me outline my talk. In the first part, I will kind of start to get an intuition, what should this finiteness structure be, right? And the way how I do this is I will talk about the complex structure moduli space and flux vacuum. So this is something which has been studied for quite some time, and we made some nice progress, I believe, in the last couple of years. And I want to tell you what are the lessons about the complex structure moduli space and flux vacua that we learned in our study. And to give you an upshot of the statement is, well, the statement is that scalar field spaces and scalar potentials which arise in type 2B flux compactifications are remarkably constrained. So they're by no means random potentials or anything like this. Yeah, so they are very constrained, and I will try to explain what these constraints are and then abstract them into general constraints. Then these remarkable constraints on the scalar potentials, they allow us to actually show the finiteness of flux vacua, of self-dual flux vacua. And I will already give you some hints on the structure of the vacuum landscape in flux compactification. And if you look at the proofs, it's quite amazing that the structure is, or the information is just enough to ensure finiteness. Yeah. So it doesn't have to be there. It's not a simple argument. It's a very non-trivial argument, but it just works out fine. And finally, I want to tell you about the tameness of the landscape and promote it into a principle. And for this part, I will have to introduce you yet another quite involved mathematical machinery, but it's a very fascinating machinery. I'm also not a full expert on these things, but I'm learning every day more on it. And this is actually the theory of O-minimal structure on Tame topology. And this is also what we used in this finiteness proof. Okay, so let's get started. Flux compactification, some lessons that we learned over the years. So let me first explain what are flux compactifications. I believe that many of you have seen it, so I can be very brief, and we also heard about that yesterday. So we study type 2b flux compactifications. We switch on some background fluxes, which are integral three forms, and we have a tadpole constraint, which is like this. Now, as you might know, these three forms can be combined into a complex flux with the dilaton axion tau, and then the vacuum condition is the following, namely that the Hodge star of G3 is I times G3. So the flux has to be imaginary self-dual in the vacuum, right? So this turns out to be also a consistency conditions onto the 10-dimensional background if one studies type 2b orientifold compactifications. The nice thing is that this kind of condition and this kind of setting actually lifts naturally to F theory. In fact, that's where we should study it because it's so much more powerful to just go one dimension up. And in F theory, the flux is not a complex flux, but a real flux. So G4 is actually itself integrally quantized or half integrally quantized. And it's also constrained by a tadpole condition of this form. The vacuum condition takes this form, namely that the Hodge star on G4 is equal to G4, right? So this is the same condition like this, but in an F theory setting. And we want to study these flux vacua in the following. Why do we want to do that? Well, because this setting is really well justified, right? So this is a very well studied set of n equals to 0 and 1 vacua and it is known from examples that some complex structure moduli can be fixed from this. The back reaction is under control, higher derivative corrections can be consistently included. And I think it's fair to say there is no minimally supersymmetric setting which has been studied to this much extent, right? So this is our motivation, or that is our setting. And so why, when I say it has been studied a lot, that means mostly in examples, but so why is it complicated to get general insights about this? Well, you have seen, I talked about this flux vacuum condition, and there the Hodge star appeared. And this Hodge star changes over the complex structure moduli space and the complex structure moduli space, but also the functional dependence of the Hodge star on the complex structure moduli is very, very complicated in general, right? So what people did is they said, well, but then let's use the fact that the effective theory is actually supersymmetric, that it's n equals 1 supersymmetric. So what does that mean? That means that we can formulate the scalar potential, but everything else in the theory via a scalar potential and a superpotential, yeah, and a gauge coupling function. And this scalar potential and superpotentials are now defined in terms of this unique d,0 form on the Calabi-Yau d-fold, so 3,0 form on Calabi-Yau 3-folds, and this flux GD, where G3 was complex and G4 was real. And then the vacuum condition is actually just a condition that the F terms vanish, right? At least the F terms for the complex structure moduli and the dilaton axion in n equals to in Calabi-Yau 3-folds, right? In Calabi-Yau 4-folds, it's just complex structure moduli. So this is the same. If you evaluate this, this is the same condition as having self-dual fluxes. So why does that seem to be easier? And in some sense it is, namely everything is now formulated in terms of the so-called periods of omega, namely the integral of omega over 3 or 4 cycles. These are now holomorphic functions or sections, and they are constrained by holomorphicity. Yeah. Nevertheless, they are complicated transcendental function, and they are hard to compute, even for examples. Yeah, they are very hard to compute in many cases. And it's even harder to see any properties by staring at them. Yeah. But that's not the way how we want to proceed. We don't want to go through specific examples, but we want to take general conclusions about the moduli space. And the way how we will do it is we say, well, the complex structure moduli space actually has a non-trivial structure, and it has boundaries, and therefore it has asymptotic regions. And so the minimal hope which we can have is to learn something about the periods in these asymptotic regions. Let me give an example. So for the moduli space, for the mirror quintic, is just a two-sphere with some special points, and these special points include, for example, the Conifer point or the large complex structure point, and these are exactly these sort of boundaries I'm talking about. And the near boundary regions, where we can hope to study our system in general, not for specific examples, are then these kind of regions near the conifold or near the large complex structure. Maybe it's interesting to point out that we are talking about holomorphic functions, so these regions will be these places where the holomorphic functions have singularities, and this is actually the important information about the holomorphic function. That's one of the important informations about holomorphic functions. Now you might say, why are we interested in asymptotic regimes? Well, in string compactification, we work always in an asymptotic regime. For example, we work in the large volume regime to gain control, or most of the time we work in the large volume regime. And by mirror symmetry, this is exactly the dual of this region here. So if we learn something about the dual of this region, that's always useful for our study of string compactifications. Now, unfortunately, the picture is not quite as simple as it is for the mirror quintic, but in general, the boundaries of the moduli space can form a really difficult, complicated net of intersecting subsets of the moduli space. And I give you here this example, and you see the conifold locus has some very non-trivial intersection with other boundary loci and so on. So in higher dimensions, we expect that this study will be orders of magnitude more complicated. And in fact, that's one of the main lessons you also can take home from my talk, is that when you learn something from a one-dimensional case, if you go to higher dimensions, it will be much, much more complicated. So now we want to get a systematic understanding of these asymptotic regions without going through examples, identify flux vacua. Maybe we can also test conjectures. And in fact, that's what many people did also exactly in this setting or a similar setting. And I refer you to some excellent reviews on this, and also some papers which maybe have some of the closest overlap with what I'm going to say in the following. So what kind of technique did we use in order to kind of get these general results? Well, we developed tools in asymptotic Hodge theory and applied them to test conjectures, and in the finiteness case, we applied them to prove conjectures, to prove a conjecture. This is already started some time ago, as you might know, but I should alert you that only more recently we kind of get a full understanding how powerful this actually is, and I hope I will convince you of this in the first part of my talk, namely in the specific lessons which we learned. Yeah. So let me first say the first lesson, quickly sketch this. Well, first of all, we understood that on each of these boundaries, there is a PQ decomposition, and a decomposition into SL2C to the n representations. So for every boundary, you can associate kind of something like a Hodge decomposition in PQ types and an SL2 to the n group and its representations. And the representations which will appear on the boundary kind of is specific to the boundary in complex structure moduli space. And this you can do for every boundary which occurs. Yeah. And the codimension n boundary gives you an SL2 to the n. Yeah. So let me just explain this quickly for a Calabi-Yau threefold, where I send one modulus to the boundary, then there's just a single SL2. Then there is on the boundary a PQ decomposition like this. This you have seen before, but I alert you, this is now a very non-trivial statement, because on the boundary, the manifold is wildly singular, right? These boundaries are the conifold point. The boundary is the large complex structure point. At the large complex structure point, there is a PQ decomposition. And then there is also an SL2 decomposition where we can introduce SL2 spins and highest spins. So this is something which we know very well from physics, and then classifying these allowed representations allows you to classify the boundary. So we get, for higher dimensional cases, we get multiple SL2 spins, and in fact, you can assign really multiple spins to one for one boundary. So I mentioned it already. This gives you a classification of boundaries using SL2 representation theory and some positivity constraints. So just to kind of sketch a little bit how what is kind of the outcome of this, you get for one modulus cases, you get 4 types, so mild degenerations, and then 3 principal times of what kind of can happen at a singular point in this complex structure moduli space. In the 2 moduli case, it gets already much more complicated, and there are in 16 non-trivial cases, and then there are the mild degenerations, so similar to this, plus the 1 modulus cases. So in total, one has something like 20 cases. Yeah, and just to stress this once more, whenever you do any computation in any example, it has to fall into one of these cases. Yeah, so there's no way out. And in fact, I can assign some recent papers. I can say what kind of cases they have studied. Yeah, so these cases have been studied here. These are the Seiberg-Witten theories, which also have appeared in some recent papers by Tame and collaborators. And then the large complex structure cases, of course, all appear in the Kreuzer-Skake list. So every case you find, you can put into this list. Okay, and don't worry about the names; these are just labels to these various boundaries. Now, the second lesson we learned is that it can be useful to directly approximate the Hodge star near the boundary. And in fact, the approximation of the Hodge star is given by the SL2 spins. Yeah, so this is another result from asymptotic Hodge theory, namely that the Hodge star of a form actually can be approximated in this way if you go to this limit where these y's are very large, so they are close to this boundary point. This is a very crude approximation, but it's extremely easy to handle, because you're just dealing with algebraic polynomial equations. Yeah, so if you're looking for vacua, as I will discuss later on, you just have to solve polynomial equations, and that's for a computer, that's very easy. Yeah. Now, more recently, we understood that this technique is even more powerful, namely that in the asymptotic regimes, you can even reconstruct not only the leading Hodge star, but the also subleading corrections to the Hodge star, and also the periods themselves. Yeah, and this can be done solely from the boundary data. So you specify some data to the boundary, specifying the boundary, and then you can use this to reconstruct the periods into the bulk. Yeah. So what kind of data you need? You need the SL2 data, which I already told you they are classified. And in fact, you can write down simple normal forms. And what you then also need is some additional information, which we call phase operators. They have some specific meaning in Hodge theory. And we can make a general ansatz for them because we know their properties. And if you put all of this together, you can reconstruct the periods near the boundary. So this is mathematically reasonably involved. But what you find then is that every period which you get close to this boundary has a polynomial and some exponential instanton corrections or essential exponential corrections. We call them instanton just because they remind you of instantons. This is just geometric. Everything is geometric here. So in fact, at most boundaries, you find these essential exponential corrections, and you need to include them because they are, for example, required to ensure the non-degeneracy of the moduli metric. So if you're not a large complex structure, it's very crucial to realize that you cannot work just with polynomials in the periods. You need to include exponential corrections, and you can compute them using these Hodge theory techniques. Let me show you some examples. So this is the one, these are the kind of the general models which you find using these Hodge theory techniques. In the one modulus case, there are these finite distance case, which is, if you look closely, are the conifold periods. Then in the type 2 cases, the infinite distance cases, then you find these periods, and then you can imagine that if you go to higher dimensional moduli spaces, this gets really complicated. But the remarkable thing is, without using examples, you can do it. Yeah, so there is an algorithm to do it, and this is the result which you find. So for each boundary, you can now write down the periods near this boundary in a specific form. So here I write down the ones for the type 2 boundaries. So this is just a name. The Seiberg-Witten boundaries. Now you might say, well, but what is this useful for? Well, first of all, I told you it's essential instantons, so you need them. Yeah, you cannot get away without using them because everything will be kind of degenerate and singular. So but there are also practical applications, as we showed in the paper which appeared on Monday. Namely, one can construct a vacua with exponentially small superpotential. And this has been done before, and there was a nice algorithm suggested in these papers here, especially the first paper, and they carried this out near the large complex structure and the conifold point. And what we succeeded in is kind of to explaining now how one conceptually understands this construction in asymptotic Hodge theory near every boundary, not just in these specific cases. And we also show we construct new vacua using essential instantons. In fact, one should say that in Hodge theory, this kind of settings where you have these exponentially small quantities, they have been studied, and they called it the extended locus of Hodge classes. In either case, in any case, the strategy now to construct such vacua is the following. You take your split of your periods into these polynomial pieces and these essential instanton corrections. You also split the Kähler potential and the superpotential accordingly. Remember, we can compute them, right? We can construct them explicitly. And then you look for vacua. And the first idea you could have is, well, let's just look for polynomial vacua and then say, what can happen is you get exponential corrections, so you get only exponentially suppressed correction to this story. The fact is that this is not true because derivatives and kind of dropping exponentials does actually not does not exchange. So these essential instantons are essential because if you take derivatives, they actually kind of are important and they become polynomial corrections in the lower level, so to say. So, and that's exactly what happens in these type 2 points in this example, which I showed you the slide of, in these Seiberg-Witten points, and consider this sort of scalar potential, which you get by just plugging in the periods, which I showed you before, and it has an instanton correction. And you see immediately that if you compute the metric from the polynomial piece alone, it is it's just singular. Yeah, the Kähler metric would be singular. So these instanton corrections, these exponential corrections are needed, and therefore we call them metric essential, right? They are needed to ensure the non-degeneracy of the metric. And now we realize that the Kähler potential and also the flux superpotential has these polynomial and exponential corrections. And now we can solve these vacuum conditions, and they in fact become polynomial, right? Because these exponential corrections, if you take the derivatives and you drop over all exponentials, become polynomial equations. And what we then find is that indeed these exponential allow you to find explicitly vacua which have an exponentially small superpotential, but polynomial masses for the moduli. And it's exactly because of these exponential corrections are these metric essential instanton corrections. And in fact, this fits very nicely with the result that the Hodge norm in asymptotic Hodge theory is polynomial. Yeah, and that's how this can work. So despite the fact that there are exponential corrections in the periods, the Hodge star can still have a leading polynomial piece because the exponentials cancel.
Question.
So you see is there a question?
Yeah, sorry for interrupting your flow. I just want to make sure that at least here you call this essential instanton is came from the worksheet, right?
So can you repeat the second part, please?
I mean, I just want to make sure that here the essential instantons came from the worksheet instanton, right?
That's where we picked. That's where we picked the name from. In large complex structure, large volume, there it's indeed these instantons would be kind of worldsheet instantons. The unfortunate thing is that at large volume, there are no essential instantons, as you might know, right? So at large volume, you can just drop the instantons and your metric is still okay. The point is that if you go to other points in moduli space, in complex structure moduli space, where these are just exponential corrections, you cannot drop them. Yeah, so at large complex structure, you can drop them. At other boundaries, at most other boundaries, actually at all other boundaries which we showed, you cannot drop them. Otherwise, you find inconsistencies.
Yeah. Okay, thanks.
Yeah, so remember, we are on the type 2b side, so these are not worldsheet instantons. The mirror would be worldsheet instantons. Okay, and finally, one can kind of make a full story about modular stabilization using these asymptotic Hodge theory techniques. Namely, we can now use the other lessons to study this vacuum condition systematically. I told you already we did this for the small superpotential, but you can now promote this to a kind of an approach to modular stabilization. So namely, what do? You first study modular stabilization in this asymptotic regime using the SL2 approximation. So if you go deeper and deeper into the moduli space, this approximation will become more and more crude, like kind of it will fail, there will be corrections. But the closer you go to the boundary, the better it will be behaved. Yeah. But you can do it as a first step, and it's actually quite easy to implement because I told you it's polynomial, right? So a computer can easily do it. The next thing is you can include these exponential correction, these essential exponential corrections. mathematical terms, this is called the nilpotent orbit. And then you can find a refinement of the SL2 vacua. And finally, we don't do that because that's quite involved and you really need examples. Yeah, you can compute the full periods and then you would find the exact vacuum. But these two steps here, the first two, you can do abstractly. Yeah, because they are fully within the framework of asymptotic Hodge theory. But of course, you then have free constants in there, which you can then determine from example to example. There are many interesting things happening in such a moduli stabilization scheme. For example, a flat direction in the SL2 approximation might be stabilized in the second step. Yeah. So this is a very algorithmic approach to stabilize moduli, and it can be done abstractly or for examples, and even for examples, it has favorable numerics as we show in our upcoming paper. And we can implement hierarchies, this I already explained, and it is also works because it's abstract and algebraic. It can also work for a large number of moduli and fluxes. And this is, I believe, a very powerful tool to address the tadpole conjecture, which was yesterday discussed in Joseph's talk. Okay, so this leaves me at the end of the lessons. Now, I want to spend the rest of the talk to explain how these tools, which we learned from this study, can be useful to actually prove something, namely the finiteness of self-dual flux vacuum. I remind you of the question. This is the question. It's a mathematical question. You want to have integral fluxes which are self-dual and satisfy this tadpole condition, and we fix the Calabi-Yau manifold for this discussion. So we're not proving finiteness of Calabi-Yau manifolds. There have been evidence for the finiteness of flux choices by Douglas and collaborators in the past, and I don't want to discuss this in detail, but they never really showed it, right? They put out a number and then people thought, oh, this is clear, but it's actually, it was an open question and actually quite surprising to the mathematicians I worked with that this should be true, and now it's shown to be true. So this is a very hard mathematical problem. One cannot stress enough how hard it is, and you will see later on why it is hard a little bit. So first you could think, oh, this is a very simple mathematical problem because, well, the tadpole conditions and combining it with the self-duality condition, then you write the tadpole as something positive. So, and this is bounded, so you bound something positive with a number, and so you think of it, this is the flux lattice, and then you draw a circle, and since this is kind of something positive norm, then it's just some circle, and then you just count the number of vacua, and that's the answer, right? So it's obviously finite. The problem is that this is not a statement for a fixed manifold, right? For a fixed manifold, it's trivial, but if I allow the manifold to change shape, then it becomes a highly non-trivial statement. Namely, this Hodge star can degenerate, right? It can develop a singularity, can become arbitrarily small. And if it becomes arbitrarily small, the fluxes appear to be able to become arbitrarily large. Yeah. And so you think, oh, I can put more and more flux. Yeah. But the point is, this is not possible. And the way how to show that it's not possible is you have to control the Hodge star and the periods or the periods, if you want, near the boundaries of the moduli space, because that's the only place where the Hodge star can degenerate. Inside the moduli space, the problem is trivial. And by the way, many of these problems are like this, right? So they are inside the moduli space, they are trivial, but if you go to the boundary, that's where the whole story happens. Yeah. It's about what is the compactification of the modular space. So the first idea would be a direct approach. You show that on every path to every boundary, only finitely many vacua can exist. Yeah. So this would be the first way to do it, and you use the SL2 techniques to do it. Now, this can be done, and in fact, you need the full power of the SL2 asymptotic techniques. And this you can find in my paper from last year. And if you want to understand what's really behind this, I encourage you as a start to read that. I hope it's comprehensive, because you need to acquire a little bit of the, not a little bit, quite a lot of this SL2 asymptotic knowledge. Yeah. But it can be done, and it's really remarkable. You see that all the bits and pieces, they come together precisely such that you can never escape to an infinite amount of vacua. Unfortunately, and that's, I told you, is one of the lessons, the general story with more moduli is orders of magnitudes more complicated. Yeah. I should mention there is a famous theorem by these famous mathematicians which show this for 2,2 fluxes. Of course, they don't care about fluxes, but they study so-called Hodge classes, which are what we would call 2,2 fluxes, namely integral fluxes which are 2,2. Yeah, and this paper is so famous because it's kind of viewed as the strongest evidence for the Hodge conjecture, and that I tend to always bring this up, but it just is meant to indicate to you that this is not a trivial question, right? These are very, very non-trivial questions. And what do? They are very ingenious people. They use these SL2 techniques for multiple variables and indeed control every path to every boundary, not just for Calabi-Yau, but in general. But they use holomorphicity in a specific way. And so for them, it's important to have these 2,2 fluxes or P, P forms on a Calabi-Yau P-fold. The general proof is more involved, and it actually uses some recent breakthrough where by Bakker, Klingler, and Zimmermann, which connect Hodge theory, so the things which we discussed, with another mathematical field which is called Tame topology. And just to sketch a little bit what they suggested is, what they found, what they proved, is that the period map, so these are the periods which I used, but there is a more fancy formulation of this, is actually has specific properties. First of all, they showed that the place where this period map ends, these kind of quotients, these arithmetic quotients, they have a Tame topology. I will indicate in a moment what that is. That the period map is by no means a general map, right? It has holomorphicity properties, but even then it's not general, right? It's a very special map, which is Tame, yeah? And they use these SL2 techniques to show that. And then they give an alternative proof to this theorem of this famous theorem on Hodge classes. Okay, so what does that mean in like a more physicsy, very rough sense? It's a statement that these arithmetic quotients can be covered by finitely many patches and can be glued together in a nice way, and that the period map is mapping finite sets to finite sets. This is a rough way of thinking about this tameness. So now we can ask, what about the scalar potential, right? And that's exactly the sort of question we want to answer, namely if there are finite many solutions. So finitely many solutions to what? Well, we know that the scalar potential can be written like this, so as an absolute square, and then a self-dual flux actually is a zero of the scalar potential. Yeah. So what we want to show is that there are only finitely many zero sets. That's what we want to prove, right? And that this is non-trivial is because there is an infinite flux lattice, which is appearing here, right? You can pick infinitely many fluxes, and these. So in principle, this is a function which maps an infinite set to an image. Yeah. And what we show in this upcoming work is that in fact this combined thing has this finiteness property preserved if one imposes the tadpole bound. Yeah, so that this is kind of this sort of is also some sort of Tame function. Yeah. So what is the statement of the finding is that if you have your moduli space and your flux lattice, then there are only finitely many choices. So you have a choice in the flux lattice, and this might give you a vacuum, which might be point light in the moduli space, or it might be of higher dimension. So there could be one modulus which is unfixed. But the point is, these sets, there's just finitely many sets of this type. So you can have finitely many choices in this lattice, which give you finitely many subspaces of the moduli space. And that's the statement of this finiteness theorem. Now I mentioned a couple of times that this uses kind of this Tame topology minimal structure. And so I should tell you in the last, I think I have something like 7-8 minutes. I want to tell you a little bit about the minimal structure of the landscape. So now, so if you are not interested in flux compactification, then you should wake up now. What is the mathematical structure behind this? Well, it's the idea of developing a mathematical framework which somehow respects finiteness properties. Yeah, and it also removes kind of pathologies which occur in an ordinary topology. Yeah, and in fact, this was envisioned in one of Grothendieck's famous essays, in 84, sorry, the German thing, 84, and it's called Tame topology. And this led more recently in the 90s, it started in the 90s, and many of the famous results were just proven recently, led to the theory of O-minimal structures. They give a generalization of semi-algebraic geometry. So we use a lot of algebraic geometry, but this is kind of a more general framework which especially gets rid of many of the things which we like holomorphicity also plays no role there. Yeah. And if you want to read a little bit about this is some book which I can recommend, but there are also very good review articles. So now recall, what is the question? We want to ask the zeros of some function, which depends on this kind of, on these t's and on the fluxes. And in order that this has only finitely many zeros, then it's very clear that this function has to be special, right? It cannot be a general function, because you can easily cook up functions which do not have this property. For example, take the sine function of phi minus 1, and if you go close to phi to 0, this has infinitely many zeros, this function. Or you take this function here, and it also has infinitely many zeros. Even so, they kind of get squeezed smaller and in smaller and smaller regions. Yeah, and this was discussed long ago by Acharya and Douglas, this sort of function, and they tried to come up with arguments why they should not be fine and so on. But what one actually finds in this proof here is that these functions just never occur. Yeah, in these flux compactifications at least. So the theory of O-minimal structures gives a precise answer to what this special property is. Yeah. Now, I cannot give you in such a short time an introduction to O-minimal structures, but just to give you some intuition of what this amounts to. Well, on the real line, you can easily imagine what these finite structures are. So these are consisting just of finite number of points, finite number of intervals, and so on. And the tricky part is to extend this to Rn, to higher dimensional spaces. So the intuitive requirement is to include projections to R, which give this type of sets, and then allow for finite unions, intersection, products, and so on. And there is the general description of the structure. We don't have to read this in detail. I don't have time anyway. So the fact is, there is a well-defined definition, and it's a very powerful definition to extend this to Rn. It's a new way of doing topology. And then once you give this, then you can define what you mean by a tame function. Namely, a tame function is where the graph of the function is within this finite structure, or in this structure with these finiteness properties. And then you can prove remarkable theorems, for example, that such a definable function always has finitely many monotonic pieces. Yeah, so there is always kind of a finite decomposition, and then in between the function is monotonic or constant. Another consequence is if you have a function which is definable and holomorphic, it's just a polynomial, it's algebraic. The remarkable things is there are non-trivial examples of these structures. So that's where the story now really begins. Namely, there are non-trivial examples of these structures, and they are defined by what kind of functions you can add. And so you can add polynomials, okay? This is actually part of the definition of such structures. But you can also add real restricted real analytic function, and you can add exponential functions. And exponential function is crucial for us because, of course, we talked about essential exponential corrections. So the structure has to have the chance to include exponential functions. And in fact, there is a combined structure which has both analytic and exponential functions in it. And the period map, so the thing which I discussed before, is one of these definable functions. So then to close my talk, let me end with a conjecture. Now, given the success of understanding that the complex structure moduli space, the flux vacua, live in such a structure, in this abstract but restricted framework, it seems very natural to conjecture. Yeah, that's what we do in the swampland sometimes, to say, well, maybe the landscape in general is of this type. Okay, so I now combine the effective theories by recording their moduli space, rank of gauge group, matter spectrum, and so on. And I claim that the string theory landscape built out of this information is definable in this O-minimal structure. And all the coupling functions of the effective theory are actually definable as well in this function, in this structure. So they all respect these finiteness properties. And so finiteness is by no means just a yes or no statement. It actually constrains every function which you have in your theory. And this is, I think this is, if true, that would be remarkable. Yeah. So that brings me to the end. With the conclusions, we uncovered some structure of the complex structure moduli space using asymptotic Hodge theory. Well, the idea was that we don't have to scan through Calabi-Yau examples anymore. Then we argued that there is a new finiteness result. I didn't explain you the proof. Don't misunderstand me. I just gave you some hints. The proof is quite lengthy and technically involved, but it can be shown. And then I suggested to use this O-minimal structure to describe the string landscape in general. Thank you very much.
Thank you very much for the nice talk. Are there questions?
May I ask a quick question, maybe? So about this Tame function again, just to, I'm not sure whether I got it right. So I'm trying to picture what it is actually. So you said like examples of this Tame function is like analytic and exponential, or are you saying they are all that can happen here, or what exactly? I mean, I didn't get actually.
Yeah. So no, this is understandable because I'm always, it's very tricky to introduce this in such a talk, but I think the best way of thinking about a Tame function is this kind of theorem which I recalled. So this is the best way of thinking of a Tame function, namely, this is a proof. This is a theorem, right? This is a consequence of this Tame function, that every Tame function from R to R, or from some interval to R, can be split into finite can be split in a way that you divide the real line into finite number of intervals. And then on this finite number of intervals, the function is monotonic and continuous. So the function can be can have non-continuities. I don't know what's the precise English word, where it's kind of jumps, but only at finitely many places. So there are finitely many jumps allowed. Yeah, but in all the other places, it has to be monotonic and continuous. Or yeah,
but it does have a global expression as some.
It's a global statement. Yes, it's very important that it's a global statement. Yes, so you can write it down. These this is these are all the functions which can occur in these structures. Yeah.
Okay, thanks. Maybe I want to know more about it maybe later.
And that's, you see, a polynomial immediately satisfies this.
Sure, yeah.
Yeah, a polynomial immediately satisfies. The sine function doesn't satisfy this.
Yeah, infinitely many.
Right, because if you have infinitely many, like minima, if you want. And so it violates this theorem, so the sine function can never be a definable function. But if you cut off the sine and you just look at one period of the sine, it's definable. So it's a real analytic function, but it's restricted, and therefore it can be definable, and so on. So you see, it's a huge framework. Yeah, but if you combine these ideas with what we have, you find restrictions. So you see, I ruled out the scalar potentials, which Douglas et al. Discussed. They can never occur in these settings.
But why did it have to be a Tame function to begin with? Sorry, maybe.
Say again.
Why did you? How did you know that the potential has to be a Tame function again?
Well, for the complex structure moduli space, we show it, we prove it, and we prove it using. Of course, it's very difficult to prove this. You have to use these SL2 techniques because the Tame. So now you have to check every period if you want. Yeah. And checking every period is what they did in their famous paper, right? They showed that the periods themselves are Tame functions, and so they have very restricted properties. And please, I mean, the important thing is, of course, in the periods there are exponentials, and you might think, oh, there are sine functions coming in, right? They are the complex exponentials, so. Cosine and sine is not something which you would not come up as a string theorist.
Can I ask Can I also ask something very stupid? I mean, what goes wrong if there are infinitely many vacua? No,
well, nothing goes wrong per se, right? In the sense that they just certain like statistical arguments. You cannot make any statistical arguments in a meaningful way, for example, right? If you have infinitely many vacua and you say half of them have certain properties, that's meaningless, yeah. But of course there's no strict reason why this should be ruled out. Of course, you might also argue that kind of the predictability of string theory depends on how many vacua we have, right? That was the standard argument. If you have one, then there's a higher predictability. If you have infinitely many, then you might think that there's no predictable statement, which is not quite true because all of these infinitely many could predict the same thing. But okay.
But from the perspective of landscape, having infinitely many things will be a good thing, no? There are infinitely many.
No, this is the whole point. From my perspective, no. Yeah, I think from the perspective of landscape, it's important to have finiteness is a very important principle, and I promote it to the principle of the landscape now. Yeah. I mean, it's from what I say, yeah. I mean, this gives you it puts some predictable power into string theory, if you want.
Okay. Thank you very much. Okay. So if there are no more questions for now, let's thank Thomas again for the very nice talk. And we will move on to the next speaker, the next talk. Yeah. So Timo, can you share your screen, please?
Hello, good morning.
Okay, so
Can
the
you
next,
see?
yeah, I can see. Can you
Okay.
just try to change to the next slide so that we can?
Yes.
Oh yeah,
It works.
everything looks good.
Thank you.
So the next speaker is Timo Weigand from Hamburg University. He'll talk about infinite distance limits in F-theory on K3. Please.
Yeah, thank you very much. And in particular, thanks a lot to the organizers for inviting me to speak in this really very interesting meeting and to present some ongoing work, hopefully to appear soon, with Songju Li and Wolfgang Lerche on the infinite distance limits in F-theory compactifications in the complex structure moduli space. And this work will be on the first step on elliptic K3 surfaces. And in the broader introduction, I will also summarize to those who have not followed this field some previous work with these collaborators. So as in the previous beautiful talk by Thomas, and as it was discussed, the Swampland program is a development in the recent high energy literature, which tries to identify criteria in order for an effective field theory to arise as the low energy approximation of a consistent quantum gravity theory. And I think we all agree that if successful, this program would have tremendous impact on different areas of fundamental physics. In fact, let me remind us that the recent burst of interest in this is at least partly motivated by our endeavor to understand early universe cosmology. Namely, one of the questions that we try to understand in early universe cosmology is how far a scalar field can travel in the moduli space within the range of validity of an effective field theory. This question is of particular importance when we think about properties of inflation. For example, can we have large field inflation and therefore a significant amount of primordial tensor modes, for example. And it was a very physical question like this, which then in fact motivated us in string theory to take this question seriously and rethink what possible constraints could arise in the moduli space of a theory as underlying the one of early universe cosmology. So this is just one example where we have indeed a direct physical question in mind that motivates this line of research. Other important questions of fundamental importance are, for instance, whether a quantum gravity theory could have viable matter-stable de Sitter vacua. We heard about this already yesterday in Benna's interesting and important talk. Another question, can we have ADS vacua within a quantum gravity with scale separation, so a separation of scales between the KK scale and the ADS scale, and many other questions of this type, but also questions that are more to the heart of directly particle physics. Are there constraints on the charge spectrum in a theory? So when we think about modeling beyond the standard model physics, are there any additional constraints that we need to take into account, or does anything go in a quantum gravity theory? Are there constraints on low energy supersymmetry breaking, and so on and so forth. So this program, even though sometimes formulated in a very mathematical way, is clearly heading towards, or at least aiming to address very important physical questions. So since the questions are so hard, it is difficult to make progress without any assumptions. And in fact, this Swampland program is known to make assumptions of two types, either in a bottom-up approach or in a top-down approach. In the bottom-up approach, one could try to find general principles to hypothesize on the existence of general principles, which every viable quantum gravity theory should encompass. This line of research then does not make any direct assumptions about the fundamental description of quantum gravity, but it tries to come up with general principles based, for example, on consistency with what we think to know about black holes or other hopefully accepted principles in high energy physics and gravity. This bottom-up approach is rather broad in scope because it's not limited to, say, string theory or loop quantum gravity, or you name it, but necessarily it is oftentimes speculative and heuristic in its arguments. And this is what has produced by now a ever-growing web of conjectures, which, even though conjectural, nonetheless exhibit a remarkable amount of interrelations and logical connections. And this is just a small, very small subset or subweb of the web of conjectures which are formulated in this bottom-up approach. In a top-down perspective, we can make concrete assumptions about the actual quantum gravity theory, what the actual microscopic formulation should be, and try to deduce consequences for the resulting effective field theories. And this, while less general, has the clear advantage that it allows for precise statements within a given concrete computational framework. And for us, this framework in this talk will be string theory. And in the context of string theory and string compactifications, this approach, in addition, offers interesting relations to mathematics, as I already hinted to at the beginning. Namely, it promotes the questions: which properties of string compactifications guarantee the conjectured Swampland criteria, whichever these are? And we just heard in Thomas's very nice talk for investigations in this direction in a particular area. So to summarize, for me, the Swampland approach would be consisting in these three pillars, or consist of the steps in between them. On the one hand, we can try to come up with quantum gravity conjectures based on general reasoning in a heuristic way, oftentimes. These arguments would then make predictions for what should happen in a concrete quantum gravity, such as string theory, and in turn, looking at what happens in well-defined theories, which we believe string theory is, would allow us to test the original conjectures and maybe develop them further. But there is then also this connection to mathematics, namely to check whether a particular general principle is then actually realized in mathematics, in string theory, requires the use of mathematics, oftentimes of high-class mathematics, in order to prove the statements. But we can also turn tables round, and if the mathematical proof is not available, can translate the conjecture about the physics into a conjecture about the mathematics, namely by conjecturing that, for instance, the mathematics of string compactifications should always be such that it guarantees certain of these Swampland criteria to be realized whenever we apply it. So this opens up a nice new arena for contact with mathematics, that we try to abstract and translate some of these Swampland ideas into statements that must then hold in generality for the mathematics underlying, in this case, string theory compactifications. So before I come to the main part of my talk, I would like just to advocate this point of view in one example. Namely, one example would be the conjecture of completeness in quantum gravity. What is this conjecture? Well, first, in a usual quantum field theory without gravity, as we all know, not every charge must actually correspond to a physical particle. The key example being even pure Yang-Mills theory, where apart from the joint representation, you would have no representations whatsoever. The completeness conjecture, however, postulates that in a quantum gravity theory, such behavior is unacceptable. In other words, every charge in the weight letters of a, say, gauge theory coupled to quantum gravity should in fact correspond to a physical state. So this is a conjecture based on, again, black hole considerations or other heuristic arguments. So let us apply, just as an example, this conjecture to theory in 6 dimensions with 8 supercharges. So 6D n equal 1,0 supergravity theories. In such theories, as we know, we have a dynamical 2 form, which couples to 1 plus 1 dimensional objects, the strings, the in general non-critical strings of the 6-dimensional theory. And while in a general supergravity, these strings may or may not be realized as physical objects, according to the quantum gravity conjecture I just cited, all of them, the entire charge letters should in fact be populated by such physical strings. These physical strings being a 2-dimensional quantum field theory in their own right, they must be well defined in order for the entire theory to be well defined. So according to this probe argument, the six-dimensional supergravity theory should be such that every such two-dimensional probe, every such string which probes the six-dimensional supergravity is well defined. In particular, it must be free of anomalies, or if anomalies are there, they must be cancelled by an inflow mechanism. And the theory must be unitary if it flows to a superconformal field theory, So these constraints on these defects, which by the completeness conjecture must be present, constrain the six-dimensional theory beyond the usual constraints which one would have in supergravity. And this was used first in these papers and then a number of papers that followed in order to derive several such constraints. And just to give one example, one of the consequences of this is that in a six-dimensional n equal 1,0 supergravity theory, the number of abelian gauge group factors is constrained. There is a sharp bound of 24. This refers to all n equal 1,0 supergravities, in particular to those with t equals 0 tensors. If they have at least one tensor or more, the bound is even sharper, namely 16, but the very sharp bound, including everything, should be 24. And this was derived in this paper by looking at precisely certain, some of these consistency conditions of the spectrum of strings in such 1,0 theories. So this physics consequence, and this is now my main point, one can translate into a mathematical statement. Namely, suppose we engineer six-dimensional supergravity theory in F theory, then we know that the rank of the abelian gauge group part is given by the so-called model-Weil group of sections of the elliptic vibration. And the fact that we cannot have more than 24 such U1 gauge group factors would imply that the number of independent rational sections of an elliptic Calabi-Yau threefold, in other words, the rank of the model-Weil group, must be bounded as well. It cannot be bigger than 24. And this is a new bound, which is new to the mathematicians. In fact, there are no statements in the mathematics literature to date what the upper bound for the rank of the model-Weil group on a Calabi-Yau and an elliptic Calabi-Yau should be. And if this line of reasoning in the physics is in fact reasonable, then we would in this way produce a conjecture for the mathematics. And clearly, when such a conjecture is out there, it's interesting to try and test it, check or devalidate it. And in fact, there is a discipline of sports in mathematics, which is the record hunting for the number of sections in elliptic vibrations. And motivated by these considerations, we could show that the current record for such elliptic vibrations is in fact given by a rank of 10. These are certain Schoen manifolds. But clearly there's a lot of room here, so a lot needs to be understood more. So all this just as one example, how these physics considerations and general constraints on the physics can be translated into also interesting conjectures, which might be interesting from a purely mathematical point of view. Now, the main part of my talk will be not about the completeness conjecture, but about the Swampland distance conjecture, which in many respects lies really at the heart of the Swampland program. Those of you who have followed the field know this very well. Let me nonetheless please take a couple of minutes to summarize this. The Swampland distance conjecture is the statement that in a quantum gravity theory with couplings, first of all the couplings should be dynamical, so they should be part of a moduli space. And second, this moduli space should allow for infinite directions with respect to the metric on moduli space in such a way that as we traverse an infinite path in the moduli space, the theory is such that in infinite number, a tower of states becomes massless exponentially fast. So more precisely, this is the situation for paths such that between starting the endpoint, such that every path in between is of infinite length. So as we go to infinite distance in the moduli space, an infinite number of states should become light exponentially fast. And furthermore, it should be such that the order of proportionality in this exponential argument here should be constrained to be of order 1. This is part of the refined Swampland conjecture. And the region where the exponential decay of the particle masses starts, or in other words, the region that one first has to traverse before this exponential decay starts, this would be this blue region. This should also be only of length of order 1 or of diameter of order 1 in the moduli space. This would then be a part of this refined Swampland conjecture. And as I said, this distance conjecture is of fundamental importance in this whole within the Swampland considerations, and it's of practical relevance, so to speak, for this whole field. For instance, one can use it to give an argument against the existence of metastable de Sitter vacua in asymptotic regions of moduli space. It's important to stress this. This makes no statement about what happens in the interior of moduli space, where, for example, KKLT or other constructions may or may not lie. The argument also gives intuition for the so-called ADS distance conjecture as another example, which would be the statement that as you take the cosmological constant in an ADS vacuum to 0, an infinite number of states should become light. And at least generally, it disfavors parametrically large field inflation asymptotically in field space. And both these constraints here are important. First of all, it's true only asymptotically. And this is something that, if anything, can constrain parametrically large field inflation. So here we make, again, the connection to my initial motivation of, say, early universe cosmology. Clearly, all this leaves a lot of room for concrete constructions, in particular constructions in the interior of moduli space. But by understanding what this region is better in the context of the refined Swampland conjecture, progress may or may not be able to be made here as well. So this is the conjecture that I'd like to discuss a bit more in this talk, the Swampland distance conjecture. In fact, given the importance of this conjecture, it has received a lot of attention in the string theory literature already. Numerous checks and tests have been made in various corners of the string landscape. And in particular, I would like to highlight here the complex structure moduli space of type 2B compactifications, about which we just heard in Thomas's talk. In this case, the states which have been analyzed would be 4D n equal 2 BPS particle states. And as we see in this still very incomplete list, there has been tremendous progress in checking, or in fact almost proving, but for sure testing the Swampland distance conjecture in this regime of compactifications. And this line of research also has important implications for moduli stabilization of flux vacua, as we just heard. And here again is an incomplete list of some of the recent papers. Good. So the Swampland distance conjecture tells us that as we go to infinite distance in moduli space, this nature of the theory should change because an infinite number of states becomes light. But it does not tell us what the nature of these states is. And it also does not tell us what the nature of the theory that we encounter on the boundary at infinite distance is. So it could be, for example, like in a quantum field theory, that on some points on this boundary in moduli space, qualitatively new types of theories are waiting for us. For example, in quantum field theory, if we go to degenerations at finite distance, then we all know that there can be strongly coupled regimes where the nature of the theory changes completely, non-Lagrangian theories, and this entire zoo of interesting theories could occur. So it is therefore of importance not only to state that the theory degenerates at infinite distance, but also into what it degenerates. So we need to understand what is the nature of the particles that become light and what is the nature of the theory as we go to infinite distance. Do we find a qualitatively new quantum gravity theory at the infinite distance? Or do we, in a sense of duality, get back to something that we already know? This, as I said, is not answered by the Swampland distance conjecture as such, but based on a representative set of frameworks that we analyzed, we in fact gave a refinement or a stronger version of the Swampland distance conjecture, the emergent string conjecture, whose content is that we always get back something that we already knew. More precisely, the conjecture is, if a quantum theory of gravity admits an infinite distance limit, then the tower of particles should be of one of these two types. Either the tower of particles at infinite distance is the infinite tower of excitations of a unique asymptotically tensionless fundamental string, which emerges at infinite distance. In this case, the theory reduces to a weakly coupled string theory, and in fact, a weakly coupled string theory that we already know, say type 2 or heterotic weakly coupled theory at the infinite distance boundary. Or if there is no such infinite tower of string excitations, then at least the leading tower of massless states should have the interpretation of a Kaluza-Klein tower. So the theory decompactifies, say, from 4 dimensions to higher dimensions, and then we would have to reconsider again whether the theory undergoes a degeneration. Of course, this will stop at some stage in 11-dimensional M theory at the very latest. So this is the content of the emergent string conjecture. At infinite distance, we either have an infinite tower of string excitations, then we have a weakly coupled string theory, or we have a decompactification, then the interpretation of the particle tower was that as a Kaluza-Klein tower. And this statement has so far been confirmed in a number of non-trivial frameworks. In particular, in those frameworks that have been analyzed, it has been shown that all those cases which are not of decompactification type are such that there exists a unique, emergent, critical, asymptotically tensionless string on the boundaries of moduli space. And showing this heavily uses the geometry and in general the quantum geometry of the underlying string compactifications, and indeed a certain conspiration of in the geometry what happens at the infinite distance to make this possible. For instance, one can show this rigorously in all F-theory compactifications to 6 dimensions in the Kähler moduli space without any restriction. Similarly, in compactification of M-theory to 5 dimensions in the Kähler moduli space, and which would be the strong coupling version of type 2A to 4 dimensions on a Calabi-Yau, again in Kähler moduli space. These are the vector multiplet spaces. For 4D n equal to hypermultiplet spaces, on the other hand, the statement has been scrutinized in this work, including also quantum corrections. Compactifications to 4 dimensions with n equal 1 include M-theory on G2, as discussed by Xu, and 4-dimensional compactifications with n equal 1 in F-theory, again in the Kähler moduli space, have been analyzed in these works. And of course, in 4-dimensional n equal 1, by the very latest, but also already for the hypermultiplets, quantum corrections play an important role. And indeed, they, to the extent that they could be analyzed, they conspire in order to guarantee this statement. So this almost concludes my overview, but let me just give you an idea of what happens, once again, in case you haven't seen this. For example, consider compactification to 4 dimensions n equal 1 of F-theory. In this case, the compactification space is the base of an elliptic vibration, so that's a complex threefold. And we can now look at the infinite distance limits in the Kähler moduli space. And first, we can look at those limits in the classical Kähler geometry, and thereby classifying the possible degenerations at infinite distance, we could show that one of 2 possible things happen. Either the theory is really a decompactification limit, or it is such that the compactification space must have a vibration structure such that the fiber of this compactification threefold is either a rational curve or a torus, so elliptic vibration or rational vibration, and such that the volume of this fiber shrinks to 0, with the consequence that wrapping a D3 brane on this shrinking fiber leads to a fundamental string in 4 dimensions, which could be either type 2 string or a heterotic string, type 2 in the case of a T2, heterotic in the case of a P1. And these then are precisely, this then is precisely the unique asymptotically tensionless critical string which appears at the infinite distance when the volume of this fiber goes to 0. So this would explain the emergent string conjecture in the classical theory. And in fact, in 4D n = 1, this picture, to the extent that we were able to analyze it, survives quantum corrections, in particular alpha prime corrections, first of all, to the Kähler potential. And in fact, these corrections are also needed in order to exclude certain regions which would lead to pathological behavior. So what would be the advantage? The advantage would be that in this picture, when going to infinite distance, we don't only observe that the effective theory, the original effective theory, breaks down, but we can actually see that a new type of regime starts at infinite distance. We go to a new type of duality frame. And in fact, this is a duality frame that is weakly coupled, so in which we can do computations. And by this line of reasoning, one can then, as a corollary, prove the weak gravity conjecture at infinite distance in these theories. In the present context, this goes as follows. The 7 branes, which give rise to the gauge sector in this F-theory compactification, become weakly coupled in these infinite distance limits. And the limits are precisely such that the dual heterotic string emerges as described, and the excitations of this heterotic string can then be proven to contain a sublattice, which in fact satisfies the weak gravity conjecture, in other words, whose charge to mass ratio is bigger than the charge to mass ratio of the relevant black holes in this theory. This involves a lot of input from the geometry, also from the black hole physics, and most importantly, again, from mathematics, because it is here that information about the nature of, say, the elliptic genus of these heterotic strings in 4 dimensions, in general non-perturbative 4-dimensional n = 1 settings enters. But all of this together then conspires to prove the weak gravity conjecture. And once more, this can be then even extended by quantum corrections, at least to first loop order, where we made a proposal for how the weak gravity conjecture would change. Okay, so this was my rather long introduction to why we're interested in the Swampland distance conjecture and what the current understanding is. But all these proofs or checks that have been done so far, be it in the Kähler moduli space or be it in the complex structure moduli space of type 2b compactifications on Calabi-Yau, they are always so far in the closed string moduli space. So it's a natural question and time to wonder if there can also be infinite distance directions in the brane and open moduli space. And if so, if the Swampland distance conjecture or its stronger version, the emergent string conjecture, are still viable in such situations. Well, as soon as one reads this first sentence here, one should certainly stop and realize that the question as such is not well posed at all, because as we all know, in general, we cannot sharply separate between open and closed moduli spaces. For example, if we consider F-theory, then the 7 brane moduli and the complex structure moduli of the compactification space, so to speak, together with the axial dilaton, are of course known to unify into the complex structure moduli space of the entire elliptic fibration, say an elliptic fourfold for compactifications to 4 dimensions. So the proper way to phrase the task is to understand the physics and the mathematics of the complex structure degenerations, but in F-theory. So once more, for a complex structure of type 2b compactifications in various dimensions, this has already been done, but this is now a rather different setup. We're interested in the complex structure degenerations of F-theory and the mathematics, but in particular also the physics. And as a first step in this talk, we will be looking at probably the simplest case, F-theory in elliptic K3 manifolds to 8 dimensions. And we will take 3 related viewpoints. First, in a PQ brane picture, we will argue that these infinite distance degenerations lead to either weak coupling limits or affine or more generally loop algebra extensions of the theory. we will then relate this to the algebraic geometry of semi-stable degenerations and explain how this PQ string picture is recovered in the theory of Kulikov models and their Weierstrass realizations. And we will give a physical interpretation, which will be backed up by duality with the heterotic string. So these are the three types of steps, which will also structure the remainder of my talk. And the main proposal in this paper to appear is that apart from general recoupling limits, the complex structure infinite distance degenerations for F theory on elliptic K3 can be characterized as follows. Physically, once more, they correspond to degenerations where some of the 7 branes, PQ branes, start realizing a loop algebra. So to this extent, it is justified to think of these infinite distance degenerations as degenerations in the brane moduli space, as this has to do with the formation of certain bound states or configurations, not bound states, configurations of branes. Geometrically, they can be understood as semi-stable degenerations of Kulikov type 2 or 3, which are obtained by blowing up non-Kodaira fibers in codimension 1. And we will recover these states from this geometric picture. And the interpretation of the tower of states is that of a dual decompactification limit, namely either decompactification from 80 to 10D. This would be, examples of this are the type 2 Kulikov models, or from 80 to 90, this is what happens in the type 3 models. And all of this has to be then supplemented in addition by the recoupling limits, which I will not discuss in too much detail. So together with the recoupling limits, this is again in agreement with the string, with the emergent string conjecture. And my main point, so to speak, will be that this complicated looking type of tower that one gets in these Kulikov models indeed have an interpretation as a Kaluza-Klein tower, thereby realizing a decompactification limit. So this should hopefully clarify the physics at these infinite distance points, at least for the general class of F theory on elliptic K3. This will be the main proposal. And now we'll go, as I said, in these 3 steps. First, the PQ branes, then I'll go to the, I'll move on to the language of degenerations, and then comment also on the heterotic dual. So, as a reminder to all of us, we are thinking in terms of F theory with 7 branes. The 7 branes are general PQ 7 branes. These are those PQ branes on which a PQ string, so a bound state of P fundamental and QD1 strings can end. And of course, the hallmark of these 7 branes in F theory is that they backreact on the geometry. They induce a monodromy, an SL2Z monodromy on the general SL2 background of type 2B string theory, in particular, when we consider a PQ brane and encircle it by an RS string, then as we go back, the RS string will come back to new object, which can be computed in this way with the help of this monodromy matrix that we can read off from the labels P and Q. This, of course, is all ancient knowledge. And it is also ancient knowledge that stacks of these types of PQ7 branes then lead to enhanced non-abelian gauge symmetry in 8 dimensions. The only such symmetries could be of AD and E type, which corresponds to configurations of these coincident type of branes. It suffices here to take a basis, so to speak, or generating set of 3 PQ branes as listed here. And for each of these configurations, one can then compute the monodromy, or in turn use the monodromy to deduce what type of Lie algebra is realized. Now, important for us is that there is, however, a second type of enhancement, namely the enhancement of affine type or of general loop type. This was discussed in this classic paper, and it is the following statement. If we start with an EN type gauge symmetry, then we can enhance it to an affine algebra and affine Lie algebra by the addition of just a single brane, the brane of PQ type as given here. In other words, if we consider this original EN configuration and let it collide with a 3,1 PQ brane, then the combined monodromy can be computed just as the product of the original monodromies, and it's easily seen to take this general form here. So it's upper block diagonal. This means that it being upper block diagonal, it has an eigenstate. The eigenstate would be the vector 1, 0, which is the fundamental string. So the fundamental string encircling this general configuration will be taken back to itself. So it is consistent to encircle this configuration with a fundamental string. This therefore gives a PPS state. And this PPS state becomes massless when the two branes, or the configuration En and the additional brane, coalesce. So we get an enhancement because we get a new type of PPS state from this encircling string. And in fact, it turns out that the properties of this new type of massless PPS state are precisely such that it extends the original algebra, Lie algebra En, to the affine Lie algebra het En, or it's a Kac-Moody algebra. The roots, the simple roots, are now the original roots together with the root associated with this string loop encircling the total configuration. This is an imaginary root which has the properties that in the root lattice, its self-intersection is 0, and its intersection with all the alpha i's with all the simple roots is also 0. And these two properties are actually key for the discussion, and they are sufficient to show that the new object that one gets by this enhancement is actually an affine algebra. So these are rank 1 enhancements, and they are possible for the entire E series, so for E8, 7, and 6, but also for values smaller than 6 with these definitions. So, for example, for E3, one can enhance to the common extension, affine extension of A2 plus A1, and so on and so forth. And this also includes the possibility of starting with 0 algebra and enhancing it to just the affine algebra het E0. These were the rank 1 enhancements. There are also the rank 2 enhancements. The monodromy analysis alone admits several options, but relevant for us is only this one. Namely, we can enhance, say, our het E8 further by addition of an extra brane, an A brane or 1,0 brane. In this case, one gets 2 types of extra junctions from that encircle the types of branes, the junction delta 1, delta 2. They are both squaring to 0, orthogonal on each other, and orthogonal on everything else. And in this way, one enhances, in fact, E8 to the double loop algebra het E9, which is the loop extension of affine het E9. So why am I telling you all this? This is showing us that there can be certain directions in the moduli space of the 7 branes which go beyond the usual ADE Lie algebras. So what's the physics interpretation? Which enhancements can occur? And how is this realized geometrically? So let me first give the general statement for the physics interpretation that we will then develop further. This imaginary root from the PPS state encircling the new configuration, in fact, does not give rise to a single PPS state, but to a tower of PPS states, namely to infinitely many PPS states, one per winding number n of z, n in z around the full configuration. So for delta 1, we get an entire PPS tower. For delta 2, we also get an entire PPS tower. And this follows from the fact that delta squared is 0. So this means that if one PPS, the one junction is a well-defined PPS state, then this is true also for n copies of it. And the interpretation is that the appearance of these towers of junctions or towers of states signals an infinite distance degeneration in the brane moduli space, quote unquote, in the sense with the caveats discussed. And in fact, these BPS towers, one per junction, are nothing but the KK modes, which are then associated with a dual decompactification in a dual frame. In the case where we have the affine series het En for n smaller or equal to 8, this signals a decompactification from 8 to 9 dimensions. And for the special case, this is a single special case of het E9, where we have a loop enhancement like shown here. We have a full decompactification from 80 to 10D because we have 2 KK modes. And in fact, the fact that these junctions in this case are orthogonal in each other signals that we have a decompactification on just a torus. And this interpretation, among others, will be backed up by the heterotic dual. So let's now try to see the appearance of these states now more hands-on in a directly geometric realization of these F-theory limits, of these complex structure limits in F-theory. Of course, the most general way to describe these elliptic K3s is as a Weierstrass model. So the physical compactification space is a rational curve. We have an elliptic vibration over it, which is given in Weierstrass form as reminded here. And F and G carry the information about the position of the 7 branes, and where their discriminant vanishes, this is where the 7 branes are located. And of course, we all know that the different type of enhancements of ADE type can be read off in the Kodara-Neron classification from the vanishing orders of F, G, and delta, which never goes beyond the value of E8, which is bigger than or equal 4, 5, and 10. Everything else beyond is non-minimal and does not appear in this list. But the claim is that also the values 4, 6, 12 or beyond in codimension 1, this is the key word here, should be included in the compactification of the moduli space. More precisely, these loop enhancements that we just recalled in the monodromy approach require the appearance of non-minimal fibers in codimension 1. And such non-minimal fibers in turn lead to a degeneration, the infinite distance degeneration of the K3, which can be tamed, can be made more tractable with the help of a sequence of blowups. This leads to a degeneration of K3 into a chain of intersecting components, the Kulikov degenerations. And our goal will be to read off the physics of these Kulikov degenerations and connect to this brane picture. So this is what we are now going to embark on. So to this end, let me first recall you of a few definitions. In mathematics, a one-parameter degeneration of K3 surfaces is a family of K3 surfaces, which is parameterized by one complex structure parameter U. So this we can think of the essential complex structure parameter that we are looking at. For simplicity, I look only at the one parameter families here. U takes values in at the disk. So this is in an open set in such a way that for values U not equal to 0, we have a smooth K3 surface, say XU1, XU2, and the degeneration occurs for U equal to 0. Now, in mathematics, one likes to combine this entire degeneration into a threefold. One thinks of a threefold whose fibers are the K3 surfaces and whose base is this parameter space, which is the open set D. So we have a threefold with fibers away from U equals 0, a smooth K3, and the central fiber is degenerate into the K3 that we are interested in. According to a well-known theorem, the semi-stable reduction theorem by Mumford, it is in fact possible to ensure by some operations that every such degeneration can in fact be brought into a semi-stable form. Semi-stable means that the central fiber is the union of a set of smooth surfaces, xi, for example, like here. They appear with multiplicity 1, so the whole situation is reduced. And the only singularities are the normal crossing singularities of these different components. This, the operations may include birational transformations on the threefold, which leave the fibers away from the degenerate one invariant, or a base change, so that's a change of parameter from U to the N, essentially. But from now on, we will therefore always be thinking about the semi-stable type of degeneration, because it can always be ensured by the operations just mentioned that we're in such a case. And another theorem, furthermore, guarantees that up to birational transformations in base change again, such a semi-stable K3 degeneration, Y, can always be arranged to have trivial canonical bundles. So the fibers, of course, have canonical bundle, but also the entire threefold can be guaranteed to have canonical bundle, vanishing trivial canonical bundle. And then we speak of a Kulikov model. And the reason why this is useful is because these Kulikov models enjoy a well-known classic classification. into Kulikov models of type 1, type 2, and type 3. According to this classification in the mathematics, the Kulikov models of type 1 occur at finite distance. They are such that the central fiber is just a single smooth reduced surface. So for example, orbifold or ADE type singularities of K3, these are degenerations that would fall into this finite distance class type 1. Interesting for us, therefore, are the remaining cases, type 2 and type 3, because these occur at infinite distance in the moduli space. In type 2, we have, in fact, the central fiber being a chain of surfaces, which now I call V0, V1 up to Vn, such that the end chains are rational surfaces, so birational to a P2, and the surfaces in the middle, if any, would be elliptic ruled surfaces, so elliptically fibered, and there's also ruling. Details are not so important. What is important is that the intersection of two such surfaces is always an elliptic curve, a smooth elliptic curve of the same complex structure model, of the same complex structure everywhere. Kulikov models of type 3, this is the more complicated class, on the other hand, are degenerate into a union of such surfaces, each of them being rational, and the intersection of them being either 0 or a rational curve. So the key point here to keep in mind, the difference is, in the type 2 case, we have an elliptic curve at the intersection, and in the type 3 case, we have a rational curve at the intersection, and this determines the difference. Now let's first look at the type 2 models to gain some intuition. It is known, as part of the theorems just cited, and the further developments, that in a type 2 model, we always find two transcendental two tori, which I call gamma I, gamma 1, gamma 2, whose calibrated volume in the limit, i.e. on x0, vanishes. And by calibrated volume, I mean the volume obtained by integrating the holomorphic 2,0 form over the transcendental 2 cycle. This already gives a hint at how the Swampland distance conjecture would work, at least at this level, namely if we consider M theory on such a family in the limit due to 0, it is clear that we expect two towers of asymptotically massless BPS states from M2 branes wrapping these transcendental 2 tori whose calibrated volume goes to 0. And since these are tori, we can wrap n times, this is a general feature, to get an entire tower of states. So per torus, we get two such, per torus, we got a tower, so we get two towers altogether. These states are there, so the Swampland distance conjecture would be happy, but in general, they will only be a subset of the asymptotically massless states, and it's important to analyze if there's more than that. So we need to understand in more detail beyond the statement what the origin of these two tori is and what the interpretation of the states is. In fact, for elliptic K3 surfaces, the E8 fibered elliptic K3 surfaces, the type 2 generations are of a rather canonical form. It was discussed in this paper that the compactification of this moduli space in fact corresponds to only two possible degenerations of type 2 type, so-called type 2A and type 2B. I'm using the notation of these papers here, so this has nothing to do, of course, with type 2A, type 2B string theory. In both cases, the K3 degenerates into two surfaces which intersect over a smooth elliptic curve. In the first case, type 2A, the two surfaces are dp9 surfaces. In the second case, there are P1 fibrations over P1, over the base, which again intersect over an elliptic curve. And the first class, of course, is known to string theorists from heterotic F theory duality, and the second, in fact, from the Sen limit. So let's look at them in more detail. The first possibility, type 2A model, would be that of this that underlies the stable degeneration limit of F theory, or in fact, which underlies F theory heterotic duality. So the situation is that the K3 degenerates. This is well known, but let me now describe it from the point of view of what we would then generalize. The K3 degenerates into two dp9 surfaces. Each dp9 is an elliptic fibration over P1. We heard about this already in the talk of Cyril on Monday in a not unrelated context. So we have an I0 fibration over P1, a dp9 surface, with 12 singular fibers. This corresponds to the partition of the branes into 12 plus 12 branes. And they intersect over the common fiber. So this intersection curve is the elliptic fiber over the intersection point of the base. And now comes the important point. Where do the two tori come from whose volume vanishes in this degeneration limit? On the intersection curve, which is a torus, we have two one cycles, SA and SB. And we can think of fibering each of these one cycles over the vanishing one cycle, sigma, which vanishes at the intersection point, which can be pinched to this and taken to the intersection point. This gives rise to two tori, gamma 1 and gamma 2, one for SA and one for SB. And it is clear that the volume, intuitively clear that the volume vanishes because the sigma can be transported to the intersection point. And these are the two tori which are guaranteed on general grounds and which lead to the particle towers in the M theory picture. But what is now the interpretation in F theory? In F theory, wrapping the M2 brane on the 1, 0 or 0, 1 cycle, of course, gives rise to either an F1 or D1 string, a 1,0 string or 0,1 string. And since we fiber this over the one cycle sigma, what we recover are, of course, precisely the string junctions, the delta 1, the 1,0 string, which encircles here all the 12 branes, or the 0,1 string, which encircles the 12 branes as well. So we have a configuration of two types of strings encircling the configuration of 12 branes, one on each of the two DP9s. And this should ring a bell. This is precisely what we saw in this double loop extension to hat E9. Namely, hat E9, as I recall, is the E8 enhanced by two more branes, so that altogether we have 12 branes. The total monodromy was 9 minus n, so this is a 1, 0, 0, 1. This is in fact the monodromy of the inverse of the monodromy of the fiber over the singular point. And the fact that these two tori exist is just a statement that we can encircle the full set of 12 branes because the monodromy leaves both the string 1, 0 and the string 0, 1 as one of its eigenvalues. So the hallmark of this is really a component with I0 fiber, the DP9, intersecting another component in an I0 fiber, so in the torus of type 2. And the physics, once more, will be that of an 80 to 10d decompactification limit in the dual heterotic theory associated with this F theory, to which I will come in a second. So this was the type 2a picture. This has now clarified what the physical origin of the torus is, and I claim it also clarifies what the physics of the limit is. What about the type 2b? This is part of this classification. So please don't be confused now in my picture here. According to the classification, this is so the x0, x0 now degenerates into x1 and x2. x1 is a p1 fibration over the base. x2 is another p1 fibration over the base. So here my first p1 is this line here, x1, that its vibration gives x1. The second p1 here, its vibration gives over p1b gives x2. These intersect in 2 points, but it turns out that these 2 points are exchanged due to monodromies, due to so-called type 3 fibers elsewhere. So this means that the intersection are not just 2 copies of the base, but 2 copies with this monodromy, in other words, a bisection. So these 2 components intersect out in a bisection, a ramified double cover of the base, which in fact is again a torus with 1 cycles sigma 1 times sigma 2. Now, in addition, since we can think of this entire degeneration as essentially 2 p1s in the fiber, we have one vanishing 1 cycle in each of these fibers. Let's call this the S1A fiber. This is what one gets in an I2 degeneration. And one can now combine the vanishing S1A fiber with one of these 2 1 cycles in the intersection sigma 1 or sigma 2. This again gives 2 vanishing 2 tori, but the vanishing now is only because of the vanishing of the S1A in the fiber, which is a consequence of the I2 degeneration. So which types of states does one get? As always, one gets the states from M theory by wrapping M2 brane on this 2 cycle. This gives the BPS states, and again we get 2 tori. So therefore 2 tori gamma I, and therefore 2 towers of states. And this gives rise to states, PPS states whose vanishing volume now here intuitively, whose mass in M theory units is proportional to the vanishing volume of the vanishing cycle S1A. But there's more. at the leading level, namely, we in addition have excitations of a non-BPS tensionless string from an M2 brane wrapping the vanishing one cycle in the fiber. This gives rise to a string, and the string tension squared is again given by the volume of this S1A. And it turns out that the interpretation of these two objects, the BPS objects given by the BPS particles and the tensionless string, is precisely as expected from the F-theory point of view. Namely, these types of degenerations are realized in a Sen limit to weakly coupled type to be orientifold. Recall we started with a situation where we have an I2 fiber. So this occurs when we take essentially the string coupling to 0 everywhere over the base. And we therefore get a type to be orientifold description, the type to be orientifold being defined precisely on the intersection curve E. And the asymptotically tensionless weakly coupled 1,0 string gives rise to a tower of states, just the fundamental string states in this type to be perspective, which sits in type to be units at the same order as the BPS particles. So the theory is that of two BPS towers, but in addition a string tower, and therefore the decompactification is not an option, rather we get an effective 8-dimensional theory. So the lesson here is that we can classify the type 2 Kulikov models for the elliptic vibration into type 2A and type 2B. And this gives rise to two physically different scenarios, either the decompactification limit, which is a realization of the double loop algebra het E9, or an emergent string limit in 8 dimensions, which realizes the type 2B or Sen type limit. Okay, so this was for the type 2. Let me go back to the original slide so that you can orient yourself. This was the type 2 case. And now we come to the type 3 case, which is considerably more involved. It is generally known once more that there exist vanishing tori, but now the point is that there exists only one vanishing 2 torus, which are called gamma 1, whose calibrated volume goes to 0 in the limit. So we expect one tower of BPS particles from M2 branes by the same argument. So the classification of these type 3 limits is much more involved. But for starters, let me give you an idea of what can happen. The simplest scenario is that we have a degeneration into several components. And one of the components here, the end component, is again a DP9 surface, so an I0 fiber over a base, but such that it intersects another component with an IN fiber. So the two bases of these two degenerate fibrations intersect at a point P. And over this point, we have the intersection curve, and the intersection curve is the intersection of these two fibers. So in the present case, this would be an IN fiber. And I'm sketching here the non-blown up version of these IN fibers. One has to blow them all up. But in the non-blown up version, the IN fiber would look like this. So what would now be the origin of the massless torus, of the vanishing volume torus? We have a vanishing one cycle in the fiber SA. We can fiber it over sigma once more. And we can do so because the monodromy is precisely of the type that allows for this 2 cycle in the full fibration. This is not true for the corresponding SB fiber. That's why now, differently to before, we have only one type of 2 tori whose volume vanishes in the limit. And in the F-theory perspective, we can understand this because now on the DP9, away from the intersection point, we have only 12 minus n branes. These are now encircled by the string that we obtain by wrapping the M2 brane on the vanishing SA cycle. This is again the 1,0 cycle. And this is an eigenstate of the monodromy matrix of E hat 9 minus n, the affine extension. And the monodromy matrix is in fact the inverse of the monodromy matrix of the IN, which characterizes the intersection point. So this is the hallmark. We have a DP9, an I0 fibration, intersecting an IN fibration in an IN fiber. And then by these monodromy arguments, one can relate the vanishing torus, which is guaranteed on general grounds, to the wrapping, or the wrapping of a 1,0 string around the brane configuration on the DP9. And this identifies the corresponding tower of states from M2 branes wrapping this torus with the tower of states that one gets from the FI node that enhances the branes on the DP9, in fact, to a hat E9 minus n. So the loop enhancement is now traced back directly to the geometry. And this will be a partial decompactification of the dual heterotic theorem. So more systematically, one can now try to classify what can occur. Recall, we are looking for complex structure degenerations compatible with the elliptic vibration. Therefore, all the degenerations at infinite distance must respect the elliptic vibration structure. So we can think of degenerations in codimension 0 and degenerations in codimension 1. Degenerations in codimension 0 can be argued, modular base change and rescalings of a Weierstrass model, always to lead at worst to degenerations of type IK over the entire base. And these are recoupling limits at infinite distance. So these give rise to Sen type limits. The interesting ones are the degeneration limits that occur in codimension 1 fibers. At finite distance, these are the usual ones that lead to ADE type singularities. At infinite distance, these require vanishing orders beyond the minimal Kodaira bound. And in fact, unless the bound is strictly violated both for F, G, and delta in this Weierstrass model, we can prove that indeed, or we see explicitly, we can prove that a succession of blowups always leads to components, to fiber components with only IK fibers. So this is a generalization, what I just showed here, just with many, many components of IK fibers intersecting. If modulo blowdowns, all IK fibers are in fact of type I0, then we have a type 2 configuration. In fact, further blowdowns can take it to type 2A. This, we give explicitly the conditions for when this happens in the Weierstrass model. And this is the situation where we have 80 to 10 decompactification. If modular blowdowns, some of the IK fibers remain of IKK positive, then we have a type 3 degeneration. Again, this is when this can occur. And at least one of the IK component will intersect an IK plus n in such a way that on the IK component, we have an enhancement to hat E9 minus n. This would be a generalization of the situation where both types are IK, but an IK intersects an IK plus n such that the same monodromy arguments go through. And in this way, we can systematically give the different cases, and they all fall to the extent that we understand it now into the scheme. I think my time is essentially up, but I would like to. Do I still have 1 more minute?
Sure.
Okay.
Yeah.
Thank you. I would like to briefly, very briefly show how this works in an example. This is not part of the classification, but this is the example. So for instance, if we start easiest case with an E7 times E8 Weierstrass model, E7 at say T equals 0, E8 at S equals 0, then we can wonder what does it take to analyze these, to arrive at these non-minimal degenerations in codimension 1. For instance, if we want the degeneration at T equals 0 in this example, then we would have to take C and D, these components, to 0 in a controlled way in terms of a parameter, which we can parameterize. And as it turns out, what will then be relevant is the vanishing behavior of the remaining components A and B. One can do this very systematically and in this way either obtain a type 2 limit, which is indeed after blowdowns a type 2A limit, or a type 3 limit precisely of the type that I advertised as a general feature. And from the resulting loop algebras and further enhancements, one can then also read off the gauge group after degeneration in the resulting 9-dimensional theory. In the 10-dimensional theory, of course, the gauge group is E8 times E8. So one can not only state that one finds a decompactification, but also say something about the model then in 9 dimensions, at least its gauge group. For example, if we take this parameter k equal to 0 here, then one sees one needs 4 blowups. We get DP9 surfaces, each with 12 branes on the 2 endpoints. This is precisely as giving rise to a hat E9 configuration the strings, the towers of states from both sides can be identified. In fact, the middle components, since they are trivial, can be blown down. So we're back in this type 2A situation. And the two towers that we get would then, as we claim, be the decompactification towers to 10Ts. If we now systematically look at other vanishing orders, we realize type 3 models by intersecting also with IK fibers. In this case, for example, one would get an enhancement that to a head E8 and something that looks like head E8 also on this side, but in fact can be argued to give rise to gauge group E7 in 9 dimensions, and so on. And this is the last slide that I want to briefly mention. Namely, I mentioned several times that we have also the heterotic dual as a checkup on the physics interpretation. Precisely in this model, we can make this very explicit. Namely, these Weierstrass parameters A, B, C, D are known to map to Siegel modular forms, which are modular forms depending on the true complex, on the two moduli of the heterotic theory, the torus, complex structure, and Wilson line of the dual heterotic theory. By using the expansions for these Siegel modular forms together with their vanishing behavior in the limit, one can read off the behavior of, in particular, the complex structure on the torus on the heterotic side. And indeed, in this way, one can confirm that the type 2 cases indeed match a decompactification to 10 dimensions, and the type 3 cases match decompactification to 9 dimensions. And finally, I said we can, using this general picture, make general statements also about the actual theory after decompactification. So in particular, we can reproduce the known classification of maximal non-abelian gauge groups in 9 dimensions by systematically classifying the possible affine extensions which can occur in this framework, and trace back all the known maximal non-abelian non-abelian 9-dimensional series to these two types of combinations of affine grains. Okay, I'm sorry for going over time. Let me be very brief. We found further evidence or support for the emergent string conjecture now for the first time in the context of complex structure degenerations of F theory, in the sense that we take into account the, so to speak, open brane moduli spaces as well for F theory on K3. And we found that apart from recoupling limits, the non-trivial infinite distance limits lead to an affine or loop enhancement corresponding to a decompactification in agreement with an explicit analysis of the geometry of degenerations via Kulikov models. And once more, this gives a direct and explicit interpretation of the nature of the towers in the Swampland distance conjecture, and I think supports the claim that at the boundaries of quantum gravity, one indeed either finds a higher dimensional theory, a decompactification, or a weakly coupled dual string theory. Thank you very much for your attention.
Okay. Thank you very much for the nice talk. Any questions to Timo?
This conjecture you have at the top, what should I take as a quantum gravity actually mean? I mean, of course, we know string theory will give us quantum gravity, but I mean, suppose somebody want to prove this statement, where would I start? Because there is only one theory of quantum gravity as far as I know. And this conjecture makes a whole lot of sense.
Exactly. So this, of course, you're absolutely right. This is, of course, also the motivation behind this conjecture, and this is clearly what we see, for example, in when thinking about 10-dimensional string theories and their relation to theories in 11 dimensions, M theory in 11 dimensions. So two things: how to prove it without assuming anything about the origin of the, say, 4-dimensional quantum gravity theory, this is of course very difficult. To prove it, you have to make some assumptions what your quantum gravity theory is. And but the statement is not vacuous. So you might think I start with the string theory, so it's clear that I get back a string theory. But this is not true, because what one has to show is that one can really identify a unique dual duality frame, a unique duality frame which corresponds to a weakly coupled string. This is far not obvious. So if you think of, if I may go, if you think of this example that I started, this particular framework. So this is in the entire framework of F theory on Calabi-Yau threefolds. So we start with a theory which is not actually described as a perturbative string theory in any way, F theory. So we could think of it as M theory on the Calabi-Yau, on the Calabi-Yau fourfold in a particular type of limit. So no actual reference to a weakly coupled string is actually made in the definition of the theory, at least via M theory. And then by tracing back the structures of this of the limit in the geometry, one finds that asymptotic states arise as BPS states, in this case the strings, which define the new duality frame. Similar statements could then be made, for example, in M theory on Calabi-Yau threefolds or others. So even if we start with with frameworks of say M theory, where no reference directly to weakly coupled string is made, then still at the infinite distance limit of the moduli space, one can find such a new theory, a dual theory, without leaving the number of dimensions. So this would be the content, and it could have gone wrong in many ways. So it could, for example, have happened that rather than finding a unique dual weakly coupled string, one finds several strongly coupled strings which all compete with one another. And in fact, for a long time, this was a worry, and it was not clear how to exclude this. But by explicitly looking at the possible degeneration features of the internal geometry, it was then possible to see how this goes. So there's a lot of, in this case, Kähler geometry required in order to actually show this, that there are not competing strongly coupled strings, for example, which define the theory at infinity then. But I fully agree, proving this without making any assumption about what your 4-dimensional quantum gravity theory is, I would not know.
Thank you.
And this, of course, is true for many of these conjectures, right? That in order to, yeah.
Any more questions? I don't see any more. So if not, let's thank Timo again for a nice talk. And I think at least we can finish the official part of this session. Thank you very much.